really get into the weeds on some of the most complex, mind-bending ideas out there.
That's right.
And today, we're going to the absolute edges of reality. Think about the most extreme places you can imagine, the inside of a black hole, maybe, or the very first moments of the Big Bang.
Places where everything we think we know about physics seems to just fall apart.
Exactly. They're not just fascinating concepts, you see. They're these cosmic boundaries where our current understanding fundamentally breaks down.
Mm-hmm.
So right now in physics, there's this deep split, a kind of schism in how we understand the universe.
You got general relativity on one side.
Einstein's theory, yeah. Amazing for describing the big stuff, planets, stars, galaxies, how gravity shapes space-time.
And on the other side?
Quantum mechanics, which is just incredibly successful at describing the tiny stuff, particles, forces, all that probabilistic weirdness.
Two incredibly powerful theories.
But, and this is the core problem, they are stubbornly incompatible.
Yeah.
They just don't play nice together.
Especially not at a gravitational singularity. That's where the conflict really blows up.
You get general relativity, well, it predicts these totally wild things there. Infinite density, zero volume.
Infinite curvature. Things that sound, frankly, impossible. Unphysical infinities.
So are these actual predictions? Or are they more like the theory waving a big red flag saying, help, I'm broken?
Oh, absolutely warning signs. That's how most physicists see them. GR is predicting these pathological artifacts when you push it too far.
Not reality itself, then.
No, it's a crisis point for the theory. And that's really our mission for this deep dive.
Yeah.
How are the leading theories of quantum gravity trying to fix this, trying to resolve these singularities?
And the really wild part, could getting rid of these infinities actually open up, well, something else? A new frontier in what physicists call subspace.
Right. Which immediately makes you think of sci-fi, doesn't it?
It does.
Yeah.
So what do we mean by subspace here? We're not talking warp drives, presumably.
Hey, no, not quite. When theoretical physicists talk about subspace, they mean very specific things. Usually, higher dimensional spacetime, sometimes called the bulk or hyperspace.
More dimensions than our usual 3 of space and 1 of time.
Exactly.
Yeah.
It could involve extra spatial dimensions, maybe curled up really small, maybe bigger, and it could even mean parallel universes existing as separate membranes or branes floating in this higher dimensional bulk.
Wow. Okay. So this isn't just about fixing a mathematical glitch.
Not at all.
We're potentially talking about completely rethinking space-time itself.
It's a fundamental reconceptualization.
Okay, buckle up, everyone. We're going on a journey from where our theories break down, right to the most speculative edges of physics.
And to really get why these new frontiers are so compelling, we need to understand the wall we're currently hitting. Like you said, GR describes gravity as space-time curvature.
Super successful, usually.
Incredibly, until you get to these extremes, like a black hole center and boom singularity. And it's crucial to remember, a singularity isn't really a point in space-time.
It's more like
An edge.
a boundary.
Exactly, a boundary of space-time, a place where the smooth, continuous fabric that GR describes just stops being well-behaved. It's where space-time, as described by GR, literally ends.
And Einstein knew this was a problem, didn't he? He wasn't happy about these infinities popping up in his equations.
Deeply unsettled, he saw them as pathological artifacts, signs that the theory was incomplete, not predictions of, some infinitely dense point. He thought the laws of physics shouldn't be arbitrary like that.
And he even tried to fix it, right? That Einstein-Rosen bridge thing.
Yeah, his 1935 work with Nathan Rosen, it was basically an early attempt to sort of surgically remove these discontinuities from the theory. His first stab at a theoretical wormhole trying to bypass the infinity.
So the problem isn't just the infinities themselves, it's how they clash with our other fundamental theory, quantum mechanics.
That's the real crux of it, particularly with space-like singularities, like in black holes or the Big Bang. These aren't just a place. They're like a moment in time, an endpoint.
Into time itself.
Yeah. In the GR description, yes. An unavoidable future moment. And that directly contradicts a core principle of quantum mechanics, unitarity.
Okay, unitarity. Remind us why that's so important here.
It's absolutely fundamental. Unitarity basically says that quantum information is never truly lost. You can always, in principle, evolve a quantum state forward or backward in time.
Like running the film forwards or backwards.
Exactly. Information is conserved. But GR, at a singularity, seems to say, nope, information just gets obliterated here. vanishes.
So one theory says information is sacred, the other says it gets destroyed.
Precisely. It's like one rulebook says the story always makes sense, and the other says sometimes the last page just spontaneously combusts. That's a fundamental conflict, a big one.
And this whole clash comes to a head at an incredibly small scale, doesn't it? The Planck scale.
That's the energy scale or length scale or time scale where gravity becomes just as important as quantum effects. We're talking energies around, what, 10 to the 19 G lengths of 10 to the minus 35 meters?
Almost unimaginably small.
Yeah, it's where a particle's quantum uncertainty in position, its Compton wavelength, becomes about the same size as its Schwarzschild radius, the point where its own gravity would make it collapse into a black hole.
The ultimate collision point of GR and QM.
That's the arena where quantum gravity must take over.
So when we say space-time breaks down there, it's not like reality itself dissolves into nonsense.
Right. It's more accurate to say GR's description of spacetime, that smooth geometric picture, fails catastrophically. Our mathematical tool breaks?
But the universe presumably keeps going.
We assume so. It's our understanding, our equations that hit a wall, and that's why we desperately need a theory of quantum gravity.
Okay, so we've laid out the crisis, the dead end. How do we get past it? How do we fix these infinities? What are the big ideas on the table?
Well, there's no single confirmed answer yet, obviously. But the two main contenders, the leading approaches, are string theory and loop quantum gravity, or LQG.
And they come at it from different angles, right?
Yeah, very different starting points. String theory kind of grows out of particle physics, thinking about fundamental constituents. LQG starts by trying to quantize gravity, spacetime itself, directly, but both aim to smooth out those singularities.
Let's dig into string theory first. What's the basic idea?
The absolute core idea of string theory is that the fundamental building blocks of everything aren't point particles. They're tiny, one-dimensional, vibrating filaments, strings.
Like little guitar strings.
Sort of, yeah. And just like a guitar string can vibrate at different frequencies to make different notes, these fundamental strings vibrate in different ways to appear as different particles. An electron is one vibration pattern, a quark is another.
And crucially, gravity fits in, too.
Yes. One specific vibration mode corresponds to the graviton, the quantum particle that carries the gravitational force. That's huge. Potentially unifies all forces in matter.
Okay, so if everything's made of strings, what happens inside a black hole? No more infinite point.
Exactly. One really fascinating idea stemming from this is the fuzzball hypothesis. It suggests a black hole isn't a singularity surrounded by empty space. Instead, the entire interior, right out to the event horizon, is filled with a dense, tangled configuration of strings, a fuzzball.
A fuzzball? Seriously?
Seriously, it's a finite density object.
Yeah.
So when stuff falls in, it doesn't get crushed to infinity, it gets absorbed into this fuzzball structure. Its information gets encoded in the new vibrational patterns of the strings.
Which solves that information loss problem we talked about.
Elegantly, yes. And here's a mind bender. For a really big, supermassive black hole, the average density of its fuzzball could actually be less than the density of air.
Wait, what? Less dense than air? How's that even possible? That seems completely wrong, intuitively.
It's because the volume grows faster than the mass for these objects in this theory. But yeah, it shatters our intuition about black holes being infinitely dense points. The journey inwards just stops at the fuzzball surface. No singularity.
Okay, my brain hurts a bit now. That's wild.
Yeah.
What else does string theory offer for singularities?
An even more profound and maybe more central idea is the holographic principle.
Holographic.
Like a hologram.
Exactly like a hologram. The idea is that all the information contained within a volume of space can actually be encoded on a lower dimensional boundary surrounding that volume.
So like our 3D universe could be written on a 2D surface somewhere.
Precisely. There's a very concrete mathematical realization of this called the ATA-CFT correspondence. It shows a theory of gravity in a certain higher dimensional spacetime, the bulk, is mathematically equivalent, perfectly dual, to a non-gravitational quantum field theory living on its lower dimensional boundary.
Okay, that's incredibly abstract. Give me the explain like I'm 5 version, if possible.
Huh. Well, imagine our universe is like a really sophisticated simulation running on a giant computer screen at the edge of reality. Everything we experience, including gravity and space-time, emerges from the physics happening on that lower dimensional screen.
So in that picture, what's a singularity? It's essentially a glitch in the simulation's projection, an artifact of the emergent space-time description breaking down. The underlying theory on the boundary, the computer screen, is perfectly well-behaved and singularity-free.
Meaning space-time itself isn't fundamental, it's an illusion.
An emergent illusion, yes, or at least an emergent phenomenon. It's not the basic substrate of reality. So the journey into a singularity terminates because of the very description of space and time as we know it ceases to be valid there. The map ends because there's no territory left to map in that way.
Wow, okay. Space-time is a projection. That really makes you question what's fundamental.
Absolutely. It suggests there's a deeper reality beneath the space-time we perceive.
So that's string theory's take. What about the other contender, loop quantum gravity? How does LQG get rid of infinities?
LQG takes a totally different tack. It focuses directly on quantizing Einstein's theory of gravity. Its central idea is that spacetime itself, at the Planck scale, isn't smooth and continuous.
It's
chunky. Exactly. It's discrete, granular, like it's woven from incredibly tiny, indivisible units. LQG describes space using structures called spin networks, which represent fundamental adders of area and volume.
Atoms of area.
Yes, there's a minimum possible area, a minimum possible volume related to the Planck length. You can't have zero volume. You can't squeeze space down infinitely small.
so that automatically prevents infinite compression.
Precisely. There's a fundamental limit. It's like trying to compress something made of truly indivisible building blocks. You can only pack them so tightly. There's a maximum possible density, the Planck density.
So if you try to crush matter beyond that density,
Mhm.
what happens?
The quantum geometry itself pushes back. It creates an incredibly powerful repulsive force that resists further collapse.
And that leads to the big bounce.
Yes, that's LQG's most dramatic prediction. Instead of collapsing to an infinite singularity, whether in the early universe or inside a black hole, the matter reaches Planck density and then bounces.
It rebounds.
It rebounds into an expanding phase. So the Big Bang singularity is replaced by a non-singular big bounce from a previous contracting phase. And for a black hole, the collapsing matter bounces at the core and re-expands.
Potentially emerging as a white hole.
That's one possibility, yes. The key thing is it's a dynamic transition, a causal process connecting a before to an after, not just an endpoint where physics stops.
Okay, so even though string theory and LQG start from totally different places,
One with strings, one with space-time loops.
they both end up saying that smooth, continuous spacetime isn't the fundamental reality.
That's a really profound convergence. Whether space-time is a hologram emerging from a boundary theory or a granular structure emerging from quantum geometry, both major approaches agree. The classical picture is just an approximation.
What do you think that tells us, that convergence?
To me, it strongly hints that we're onto something deep about the nature of reality. That space and time as we experience them are not the bedrock, but rather emergent properties of some underlying stranger quantum system. Like finding out the stage we're standing on isn't solid wood, but maybe light and shadows.
Something like that, yeah. It forces a radical shift in perspective.
Okay, so if these theories successfully remove the singularity roadblock, what lies beyond? This is where subspace comes back in.
Exactly. And while LQG tends to focus more on what happens within our familiar four dimensions, string theory, with its extra dimensions, offers a really elaborate picture of a larger cosmos. This brings us to the brain world hypothesis.
Brains again, like membranes.
Yep. The idea is that our entire observable universe, the three dimensions of space plus time that we know, might be just one 3 brain embedded in a higher dimensional space, the bulk or hyperspace.
So our universe is like a sheet of paper floating in a bigger room.
That's a decent analogy, yeah.
Yeah.
We live on the surface of this brain.
But if they're extra dimensions, why can't we just, step off the paper? Why are we stuck here? Well, according to the theory, most fundamental particles and forces everything in the standard model, like electrons, quarks, photons, they're represented by open strings. And the endpoints of these open strings are constrained. They have to live on the brain.
Like they're tacked down to the paper.
Exactly. They can slide around on the brain, interact on the brain, but they can't leave it. But gravity is different.
How so?
In string theory, the graviton, the particle carrying gravitational force, is a closed loop of string. It has no endpoints.
So it's not tacked down.
Right. It's free to travel throughout the entire higher dimensional bulk. It can leave our brain, explore the extra dimensions.
And that has consequences.
Big time. For example, some models, like the ADD model, suggest these extra dimensions could be surprisingly large, maybe even up to a millimeter across. Gravity seems so weak to us compared to other forces because its influence gets diluted, spread out across these extra dimensions.
It leaks out into the bulk.
That's the idea. Other models, like the Randall-Sundrum models, propose the extra dimensions are warped, highly curved, and that curvature also weakens gravity's effect on our brain. The point is, the brain world idea gives a concrete structure to subspace and suggests a resolved singularity might be a gateway off our brain into this bulk.
And this bulk, it's not necessarily empty, right? Could there be other sheets of paper floating around?
Yeah.
Other universes?
That's one of the most exciting possibilities. The bulk could host multiple other brains, each potentially a separate parallel universe with its own particles and forces.
Parallel worlds.
They could be completely isolated, or maybe they could interact. Some cosmological models, like the ekpyrotic or cyclic universe scenarios, suggest our Big Bang wasn't a singularity at all, but actually the result of a collision between our brain and another one in the bulk.
A cosmic car crash triggering a universe. Wow, okay. So we have singularities possibly resolved, and we have this potential subspace, this bulk with extra dimensions and maybe other brains. How do we connect A to B? How might a resolved singularity actually become a pathway?
Right, forging the pathway. Let's revisit wormholes first. Classically, they're unstable, need this weird exotic matter with negative energy to hold them open.
Stuff that probably doesn't exist or is very hard to make.
Probably. But here's a thought. What if the very quantum gravity effects that resolve the singularity also naturally generate the conditions needed to stabilize a wormhole? Could the endpoint of collapse, instead of being infinite density, become a stable tunnel?
Turning the dead end into a doorway.
Potentially. But maybe a more dynamic picture comes from the quantum bounce ideas.
From LQG and string theory.
Yeah. In LQG, the black hole collapses, hits Planck density, and bounces outward as maybe a white hole. The huge question is, where does the stuff come out?
Does it just pop back out in our universe somewhere else far away?
That would be like a one-way wormhole, or could it emerge into a completely new daughter universe? Or maybe even onto a different brain if you combine LQG ideas with the brain worlds. The bounce itself is the transit.
And string theory has a similar bounce idea, but from brain collisions.
Right. Our whole brain might be moving through the bulk and could collide with another brain or some feature of the bulk. For us living on the brain, we'd experience that collision as a cosmological event, maybe like our Big Bang or a big bounce ending a prior contraction phase.
So the gateway isn't a tunnel in our space. It's our entire universe moving through the higher dimensional space.
Exactly. The mechanism is different. Intrinsic quantum bounce in LQG, extrinsic brain interaction in string theory, but the outcome, a cosmological bounce replacing a singularity, is remarkably similar.
That convergence again suggests it might be a generic feature.
It really might be a key signature of quantum gravity to look for.
And string theory offers even more direct connections, potentially, between brains.
Well, gravitons, closed strings, already travel through the bulk, so parallel universes could gravitationally influence each other. But you could even imagine open strings stretching between two nearby brains, maybe at points where they intersect.
Physically linking the universes.
In theory, yes. That could allow energy, information, maybe even matter to transfer directly between them. And perhaps a resolved singularity, a point of extreme geometry, could be such an intersection point, a cosmic crossroads.
Okay, this is venturing deep into the speculative realm now. It's exciting, but we need a reality check, don't we? Where does this all stand scientifically?
Absolutely essential. We need a clear-eyed perspective. We have our bedrock theories. GR, QM, the standard model, experimentally verified, hugely successful, but we know they have limits shown by singularities.
Then the next level.
Are the candidate theories trying to fix those limits? String theory, loop quantum gravity, these are mathematically sophisticated, highly developed frameworks, but crucially, they are still unproven hypotheses. No definitive experimental confirmation yet.
And then there's the stuff built on top of those.
Exactly. Things like traversable wormholes, travel between universes, specific brain collision scenarios. These are often logical extensions if you assume the underlying theory, like string theory, is correct, and if you assume certain very specific, often favorable conditions are met, like stable exotic matter existing or brains being configured just right. This is the furthest frontier. Deep speculation, building hypotheses on top of hypotheses.
And the biggest hurdle is testing any of this, right?
Yeah.
The Planck scale is just so far beyond our reach.
15 orders of magnitude in energy beyond the LHC. Direct tests are likely centuries away, if ever, so physicists have to get clever, look for tiny, indirect, low-energy consequences that might be detectable.
How's that going? Is one theory more testable than the other?
Well, string theory has struggled a bit on that front. It's often criticized for not making many unique, easily falsifiable predictions for our specific universe. The prediction of supersymmetry hasn't panned out so far, ruling out the simplest versions. And the string landscape idea, maybe 10 to the 500 possible string theory universes, makes it hard to know which predictions apply to us.
It's hard to test a theory that predicts almost everything is possible somewhere.
Right. LQG, maybe because it focuses more directly on our 4D spacetime, has made some more concrete predictions. One bad one was Lorentz invariance violation, or LIV.
Mola V, meaning the laws of physics, specifically speed of light, might not be exactly the same for all observers, especially at high energies.
Exactly. The idea was that the graininess of spacetime predicted by some LQG models might affect how very high energy photons travel. They might travel slightly slower or faster than lower energy light.
And could we test that?
Yes, by looking at high energy photons from distant cosmic events like gamma ray bursts. And very recently, the LASO Observatory in China made incredibly precise measurements.
And found?
No evidence for LAV. They put the tightest constraints ever on it, essentially ruling out the simplest LQG models that predicted a detectable level of LAV.
So that's bad news for LQG.
Actually, I see it as good news for physics. It shows these theories are testable, even if indirectly. Science is working at the frontiers, finding constraints, ruling out models. That's progress. It tells LQG theorists which versions don't work and where to focus next. It's a sign of a healthy scientific process, not a failure.
Okay, so summing up this incredible journey, we started with the gravitational singularity, this breakdown point in GR and QM.
A profound boundary in our current understanding.
And we've seen how quantum gravity theories, like string theory and LQG, offer ways to resolve it. String theory tends towards termination, replacing the singularity with a finite object like a fuzzball, or revealing spacetime itself as an emergent illusion.
While LQG focuses on transition, replacing the singularity with a dynamic quantum bounce, connecting a before to an after.
And resolving these singularities potentially opens up gateways to, well, somewhere else.
These speculative subspace frontiers, manifesting maybe as traversable wormholes or black hole to white hole bounces, sending matter to new regions or universes, or cosmological bounces from brain collisions, or even direct tunnels between parallel worlds.
But we have to keep stressing these gateway ideas are built on theories that are themselves still unproven hypotheses. This is the far edge of inquiry.
Absolutely. We need both imagination and critical assessment here.
Still, the quest is ongoing. Direct tests might be far off, but indirect paths exist.
Definitely. Precision cosmology, looking at the cosmic microwave background, the large-scale structure of the universe might hold clues about a pre-Big Bang era or the influence of extra dimensions.
And gravitational waves, too.
A huge new tool. Gravitational wave astronomy lets us probe extreme gravity near black holes and neutron stars like never before. We can test GR in the strong field regime and look for tiny deviations that might signal quantum gravity effects.
So, the question remains open, but it's dynamic. Whether resolving singularities truly opens a door to subspace is one of the deepest, most compelling questions out there.
It really connects fundamental physics, the nitty-gritty of quantum fields and geometry, with those huge, almost philosophical questions about reality, the cosmos, and our place in it all.
And even if the answer turns out to be no gateways, the pursuit itself pushing these boundaries.
That pursuit inevitably transforms our understanding. We learn so much just by asking the questions and developing the tools to try and answer them. We're redrawing the map of the cosmos, one equation, one observation at a time.